Can you hear me? I'm Navid. I usually go under this avatar. If you don't know me, this is my face. And I'm in Melbourne, usually working a lot with Klima, and especially people at MIT who are developing the ocean component of Klima's new Earth system model. And I don't know if you've heard, Oceananigans is, this fluid dynamics library, which the ocean component of Klima's new Earth system model is based on. So, yeah. So I don't know if I need to, just to show you, in turbulent flows in the ocean, and in generally in turbulence, the more we zoom in, the more we see. So here you see on the left an ocean simulation at a horizontal resolution of 1/12 of a degree, and on the right, 4 times more in each direction, 1/48 of a degree. All these details are very beautiful, first of all, but also they do matter for shaping up the big ocean circulation. So we need to resolve as much of these things as possible. At the moment, climate simulations, climate projections are done at 1 degree resolution. So imagine this 100 times less grid points. We are able with Oceananigans to reach pretty good simulated years per day at this sort of resolutions, and reach climate projections now. We are envisioning climate projections that resolve all this turbulence. So I'll tell you a little bit about our philosophy and show you a little bit about Oceananigans. So when we're thinking of a new climate model, what do we need for this climate model to have? First of all, it needs to be fast, and especially because we'll have to run climate projections for many years in the future. We want to be able to run and rerun things to calibrate and find the best parameters possible for our parameterizations. So this parameter estimation, as it's called also. Definitely we want it to be fast, and also so that we can crank up the resolution as much as possible and resolve as many of these details as we can, so we don't need to parameterize them with terms that we don't even know. And the other thing we really want is to be flexible. We want to be able to be playing like Lego, as Milan was saying, be able to take out a piece of the code, put something else, take out the parameterization, put something else in, test things like that, and in order to, this would help us develop the parameterizations for the physics that we are not resolving. So, and we've built Oceananigans, and it's quite fast, we can get 10 simulated years per day at a resolution that resolves all these mesoscale eddies, all these circular features that you see here. Usually climate projections don't resolve them, and they have an ocean that looks like honey, very laminar. And we have done that by utilizing hardware, like running on GPUs, writing the model from scratch with GPUs in mind, and using novel algorithms that enabled us to overlap communication and computation, so that we can scale up, and we get almost perfect scaling up to 700 GPUs or whatnot. And then on top of that, on top of being fast, it's a really nice code, and it's really user friendly. I don't know if you've ever seen a climate model. Milan was showing some in the beginning with these go-to statements and whatnot. Usually we are there with state-of-the-art ocean models in Fortran, but we put a lot of effort in making an interface that is user friendly, so that people or users essentially write code like math or like LaTeX. And this is not just a comic code, it's an actual code that will run a simulation, a very simple one. But you can see here, for example, how I'm defining a new diagnostic. I'm just essentially writing it like LaTeX, okay? So Oceananigans, the library consists of 3 main parts. First of all, a lot of modules that are related with, finite volume calculus on on discrete grids. So that involves defining the grid, defining fields, defining operators that act on these fields, derivatives, integrals, and parallel solvers and whatnot. Then there's another piece of modules that define how you read and write diagnostics, how you have these callbacks that you can call every now and again while you're running a simulation. And these two pieces of the library can be used, they have no physics yet. So you can use them either to build an ocean model or to build a sea ice model or to build whatever other fluids model you want. And a biogeochemistry, ocean biogeochemistry model, for example. And then we have like some physics there, some like actual fluid equations, and we can simulate from things that vary at the length scale of meters, so that's a full non-hydrostatic Boussinesq model, to the global ocean circulation, and use some hydrostatic free surface model, which is typically used for global ocean modeling. And I want to finish by showing you how this is also an actual code, with some little, there's some things missing here, but this code essentially will run if you fill in these little gaps. So I want to show you how, you can, a user can build an Oceananigans simulation and then inject a neural network in it. So say we want to build a simulation and then we want to use a neural network to predict how do we force the u velocity at every time step. So what we are doing is we first of all build a grid, then we allocate some field that will be this forcing for the u velocity. We build a model, in this case this hydrostatic free surface model, and we provide this USGS as a forcing. We build then a simulation, which includes the model, all the equations, the diagnostics, we don't have them here, details about how the time stepping will be. And then we create a forcing function that will take this simulation as an input, and thus we'll have access to all the model variables and whatnot, and call a neural network, which I'm here using this LAX library, and then compute this forcing term as from this neural network. And then using a callback, as Milan was saying before, we can apply this neural network, apply this forcing at every however often we want. Here I'm doing it every time step. So it's as easy as that. So having a model that runs natively on GPUs and runs as Julia, we can incorporate neural networks like that and have parameterizations taken to the next level. So with that, I'll let you go and hear questions.
Okay then, any questions for Oceananigans? I see one here.
Yeah, thanks. It was very interesting. I have a question in terms of, we all have the intuition that you increase the resolution, things get better in terms of error metrics probably.
Yep.
But can you quantify that compared to state-of-the-art ocean models, that are, not having the advantage of having such a high resolution? How much is this improvement in terms of, maybe representing the Atlantic meridional overturning circulation, for instance, or, whatever feature you pick, for instance, this one?
Yeah, well, whether we haven't done it in Oceananigans yet, because we are missing one little piece yet, which is sea ice, in order to have a full, what we say, OMIP simulation. It's but we're hoping to have that by next February. But this type of questions that you're asking, like whether increasing the resolution and including less parameterizations and more actually resolving turbulence makes your solution closer to observations. It has been done by other models. So so that's the idea. The idea also is that because one of the big parameterizations in ocean turbulence is the mesoscale parameterization. By going to a resolution that allows us to forget that parameterization, it reduces a lot of biases in the ocean. That's the hope, and we'll have climate projections without that parameterization. It will be amazing. But hold on to your chairs. Perhaps next year. Yeah.
Thanks a lot.
Okay, then, if there is one last quick question, otherwise, thanks again.
Oh,